Well, hello and welcome back. This is Mrs. Hanson, and our last video lesson on Chapter 10, we're going to complete the last few sections, beginning with Section 7 on allylic halogenation. So in this section, we're thinking back to where we add the halogen, and we've kind of been practicing recognizing where we see the weakest bond forming the most stable radical. And it should be the site of addition. And recall, if we have a cyclohexene would have a pi bond and then 3 available unique hydrogens for the site of addition. And just comparing the bond dissociation energy, how much energy does it take to break the bond, the CH bond, we can clearly see that the allylic position, let's review that. Here's the 2 carbons that are in the pi bond. And so the one that is adjacent is the allylic position. And clearly we see that this would be the weakest bond, and so we would anticipate that would be the site of bromination. So following the pattern from our previous section and creating the most stable radical, we would expect this position, the allylic position, to be the site of bromination. But it's not what we see. And we have to think back about Section 8.9, which is the bromination of an alkene. Section 8.9 said when we have a double bond and sitting on the arrow is a bromine molecule, it will add, and just to remind ourselves, the solvent would need to be a non-polar solvent, emphasizing that if we had a water molecule, which is a polar solvent, and I know this is review, but it's always good to review. If the solvent were polar, instead of nonpolar, we would add 1 unit of bromine, but the second would add the protonated alcohol that would later then cleave off the hydrogen. And you'd end up with a alcohol and a bromine across the double bond, forming the alkane. Just a review. In this situation, what we're looking at is a bromination in a nonpolar solvent where the bromine would add across the double bond and you would get the enantiomer configurations. One would enter as a wedge, the other as a dash, and of course then its enantiomer would form across there as well, where this would be the dash and this would be the wedge. So a pair of enantiomers would form. However, what's going on here now is a competition between these 2 competing reactions. We have the ionic addition of bromine across the pi bond competing with the radical mechanism where we would initiate the reaction with a spot of energy, forming 2 bromine radicals and add to the allylic position. So what we've observed just by trying to decide what mechanism is going to be favored, it truly is the addition reaction here. And so we have to just simply use a different method to add bromine in a radical mechanism to avoid the competing reaction of addition. So we can do this easily by selecting a reagent as an alternate source of the bromine called N-bromosuccinimide. And I can hear this is going to have a nitrogen in it. N-bromosuccinimide. You're going to see that on the arrow is NBS. And that's going to be key in recognizing that this will indeed be an addition of a bromine radical across the allylic position, taking out the competing addition reaction across the double bond from the previous section of Chapter 8. And let's kind of understand what's happening here. Here is NBS. Notice it has a nitrogen and it has a bromine attached by a single bond. In a homolytic cleavage, this bond breaks. And when the bond breaks, we form a radical of a nitrogen that is very stabilized by resonance. And we form a radical of bromine in an initiation step. Then we can recall, again, our cyclohexene is then ready to begin the propagation step of adding the bromine in the allylic position. The first step is a hydrogen abstraction, where the radical of bromine that we just made through initiation becomes the reactant. We can see two fishhook arrows creating a new bond, just to show where that bond ends up. This electron and one of these two electrons forms a new bond in HBr and creates the carbon radical. The carbon radical is in the allylic position. And so that's very much resonance stabilized. Now remember, the radical that we make in step 1 becomes the reactant we use in step 2. And so here is the molecular bromine, Br2, undergoing a halogen abstraction, where the sigma bond here, these two electrons, cleave that bond, and we see a new bond form in the allylic position, and we've regenerated the bromine radical. And this will propagate over and over and over again, keeping in mind the radical we make in step 2 then gets consumed as we repeat the process. And remember, the propagation step shows us the overall equation. The radical we make in step 1 gets consumed in step 2. The radical that we consume in step 1 gets regenerated in step 2. And we have now seen the overall equation. Of course, this reaction will need to be terminated, and I didn't write that, but there would be some sort of destruction in a termination step. And so the termination step would just take out the bromine radical would work. The termination step could involve taking a bromine radical and just coupling it with another bromine radical and eliminating that radical to form a bromine molecule would end the propagation step. But thinking about the observed reaction, we had a cyclohexene from the first propagation step. We see a molecular bromine from the second initiation step forming HBr as a product in the first propagation step. And of course our cyclohexene that has now been brominated in the allylic position. So just to kind of emphasize what we're looking at in this slide, when we see an allylic position and we're trying to brominate, we cannot use molecular bromine because it will simply undergo an addition reaction. So this would not be a radical reaction with molecular bromine, but instead just a plain addition across the double bond where the bromine adds in a stepwise fashion, creating a Br wedge and a Br dash along with its enantiomer. So to control that, we take out the molecular bromine as the initiation, and we control that by using a separate or a different source of bromine. And that different source we're going to recognize as NBS sitting on top of the arrow. We have to recognize that NBS is the source of bromine, not boron. So we have decided that when we initiate the radicals here, that we then propagate and then terminate those 3 steps of any radical mechanism: initiation, propagation, and termination. So let's take a look at an example. I just pulled this one from your homework. It says, remember that the allele position is resonance stabilized, and therefore 2 addition products are found. We practiced drawing resonance structures, and let's just review that quickly. I have highlighted what we call the allylic position. The 2 carbons in the double bond, 1 carbon over is the allylic position. And we understand that that is resonance stabilized. So that means when I think about removing a carbon-hydrogen bond, the radical forms at the most stable configuration, which is a tertiary configuration. We take a look at, I'll just color code these electrons here. that one electron in the pi bond will move over to partner with the one electron from the original radical, creating a new pi bond. And the third arrow says this other electron that was involved in this bond ends up to be the lone electron at the end of the chain. So this is the two structures, the two possible resonance structures for our original compound. And now notice that we just add bromine at the site of each radical, at each lone electron is the site of a bromine. So we'll add it to the most substituted carbon, and we also add it to the least substituted carbon because each one of these resonance structures exists and it goes on to form the bromination. So we'll see two products, one from each of the resonance structures. So in a resonance stabilized allylic position, we have to consider both resonance structures and add bromine to both positions where the lone electron resides. So let's practice that. Here is a cyclohexene, and then of course the double bond is going from carbon 1 to 2 in the substituted group. Let's look to see where we would have bromine add with treatment of NBS and irradiated by UV light. So sitting on the arrow would be NBS and H nu, energy. Again, we think about the resonance structure. I can see that this particular molecule has two positions that are called allylic, but they are not unique positions. They are indeed the same. So we really just have to consider one of those two positions, that this is equivalent to this, and therefore we'll only consider one, as the product would be the same had we done both. The allylic position will have the site of a lone pair of an electron and will shift the double bond to create its resonance structure. The lone pair ends up at the terminal carbon and the new pi bond forms between the original electrons. Color code if that helps. And we can make this guy dark blue. And so now we see this dark blue electron is bonded to this light blue electron, and the other electron ended up at the chain. Now we can see the positions where we will brominate. At this first product, we can see the bromine will add at the source of the lone electron, and this would be a racemic mixture. In other words, think about the stereochemistry as you predict that. We'll have bromine coming in as a wedge, and its enantiomer would also form, where you would have it coming out as a dash and the hydrogen as the wedge. Just to remember that they are indeed a mixture of enantiomers. But you will also find a primary alkyl halide form as well from the second resonance structure. This is not a chiral carbon, so we don't see an enantiomer. And that's simply because there are two hydrogens at the end here. So just to remember that this carbon is tetravalent. Two of them lead to the same atom of hydrogen, so it's not a chiral carbon, so we don't have to consider a racemic mixture. All right, so let's put that into a practice homework question. Pulling this right out of your homework, it says, predict the products when each of the following compounds is treated with NBS and irradiated by UV light. So again, when I see NBS, and you'll see H nu to represent the energy for the initiation step, this is our clue that it is bromination at the allylic position. And we're controlling that competing addition reaction by not using molecular bromine. So the clue is bromination at allylic position and then keep in mind that if it's resonance structure, draw all resonance structures to determine all products. Okay, so let's start with that. Let's find where are the allylic carbons? Here's the double bond. So every carbon that is adjacent to the double bond, as in here, 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 and here, all of those are allylic positions. Now out of that, these two carbons don't have any hydrogen on them. So therefore, they will not undergo a radical mechanism. There's no CH bond to break. Between these carbons, they are indeed the same. There is a plane of symmetry in this molecule, so these two carbons are exactly the same, so we only have one unique allylic carbon. There. One unique allylic carbon, and that is the site at the end of the methyl group. So let's consider all the possible resonance structures. So as we do that, we have found that there were 4 allylic positions. Of the 4, we eliminated these 2 because there's no hydrogen, leaving us the bottom 2, which we then decided were mirror images. So we only have to consider one site between both of these allylic carbons because there's a plane of symmetry. Alrighty. Now, as we think about the resonance structures, we remove the hydrogen and form an allylic position to form the radical. And that's what I've done here. I removed a hydrogen and made an allylic radical. And yes, I could have absolutely made it at this site as well. I just had to pick one side or the other. Draw the resonance structure for these allylic positions. Draw the 2 possible resonance structures, and this is what we end up with. We can see the original electron, the original picture, would shift with 3 fish hooks to form a new pi bond and a radical in this position. So the site of addition of the bromine will be at the end of the allylic position here. And again, a second resonance structure where the allylic position is at the corner of the pentane house. And that will lead to a bromination product in each of those additional reactions. In other words, we have the bromine, oops, I forgot that guy there, the bromine in the allylic position here, and a second product from the radical that was in the resonance structure, giving us 2 products to draw. Just a reminder that there were some sections, atmospheric chemistry and auto-oxidation, that I put in as assigned reading, and I won't be lecturing over those sections. So we'll move right along to the final topic, the radical addition of HBr, kind of the explanation of the anti-Markovnikov addition that we discussed back in chapter 8. So a quick review of how we can explain the anti-Markovnikov addition when we see peroxide involved on the arrow. So from chapter 8, this was our alkene chapter, we said that a hydrohalogenation across a double bond is a 2-step process in which we form a carbocation intermediate by the addition of a hydrogen first, and then in the second step, we add the bromine across the double bond, and the bromine then attaches to the carbon that has the most carbon attached. The most substituted carbon is the bromine additional site because we created the most stable carbocation in that first step, the initiation there of the intermediate carbocation. So when we use a carbocation intermediate, the bromine will attach to the most substituted carbon. That's known as Markovnikov's rule. But we then decided we could find a method to brominate and create the anti-Markovnikov rule, and that's now in the presence of this peroxide. Do you remember from just a previous section in chapter 10, we said that this bond is very easy to break. And when it does so, it creates radicals. And with a lone electron on each oxygen, then that could begin to propagate in our mechanism. So the role of the peroxide is to create radicals. And let's investigate that step by step. So the initiation, we've learned, is the first step because it creates radicals. That's the job of the initiation step, is to create radicals. And we have a homolytic bond cleavage in the presence of heat that creates two alkoxy radicals. Again, an endothermic process. It requires heat. An endothermic must be have an energy input to have the reaction occur. So the peroxide's job is to undergo an initiation step in which the bond is cleaved, creating radicals. We'll then use that very radical that was produced into the next step and do a hydrogen abstraction with the goal of creating a bromine radical. So the initiation step is used to create a bromine radical. The reaction begins to propagate. The bromine radical we made from the initiation step is now going to add across the pi bond in an addition radical mechanism. And when it does so, we create a carbon radical. The carbon radical says we're going to create the most stable radical, which is this tertiary position. So the lone electron must end up in the tertiary position, making the bromine add-on in a secondary position across that alkene bond. In a second step of propagation, the very radical that we made here becomes the reactant in the next step, in which we abstract a hydrogen from an HBr. This bond breaks, a homolytic cleavage occurs, and when we do so, each electron goes in the separate order, and we create a new bond. Let's color code just to help us see. We'll make this purple and these two electrons green. Therefore, we can see the green electron is now on the bromine radical, and those original blue they were purple electrons, are now involved in this bond here. That's where they landed to create both enantiomers. So plus enantiomer here. Now, keep in mind, the propagation always gives us the net equation. So the carbon radical that was made in step 1 is consumed in step 2. The bromine radical that was used in step 1 is regenerated in step 2. And the overall equation is left as the alkene adding with HBr, forming the anti-Markovnikov addition product. So we've added the bromine across the bond, but it ended up to be in the least substituted position instead of the most substituted position. And of course, we would have to terminate to end the propagation steps, and we compare those two mechanisms. In a tertiary carbocation, we have a carbocation intermediate. However, in a radical mechanism, we have a radical intermediate. This is an sp2 carbon, meaning that this is an empty orbital. This orbital is not empty, it contains a lone electron, so there's no chance of rearrangement. In the ionic mechanism, the bromine would add to the least substituted, the hydrogen would add to the least substituted carbon in the first step, and then the bromine would add on to the more substituted carbon, giving us a Markovnikov addition. But in a radical mechanism, the bromine adds first to create a stable radical, which means the radical gets the primary position of tertiary, and the bromine adds on at the secondary position, and then the propagation would add hydrogen next. Ionic mechanism says we add hydrogen first bromine second. Reaction in a radical mechanisms adds the bromine first and the hydrogen last, and thus the difference in location of where those two molecules will end. So when I see HBr in the presence of peroxide, peroxide creates the radicals, and now we understand the mechanism to produce an anti-Markovnikov addition. And when you see that, this again looks very similar to homework you worked from chapter 8. We're just looking at building the understanding of how this reaction occurs now that we understand radical mechanism. So we look for an anti-Markovnikov addition in the presence of peroxide. The peroxide creates radicals. The radical must be stabilized, and therefore we add the bromine to the least substituted position. So the least substituted position adds the bromine across the double bond here, and remember that it will always add enantiomers to your position. So you can add the bromine not only as a dash, but also as a wedge. And that, my friends, concludes your lessons from chapter 10. You are now ready to go on and practice some problems with your Wiley homework. The Orion is available to you. In addition to that, there's some supplemental videos if you want to work some more with other voices. And then finally, your practice test as well. Good luck as you complete your lessons.